Hey coders, welcome back. So in the last video, we did I think one more assessment, and let's try to go one more, right? So in the last one, I think I took this one, the phone interview one, and the questions were related to like one was the queue related question, and another one was a binary search tree based question, right? So yeah, so let's again try to solve one of the assessment. And let's try to solve this one today. On-site interviewer. So there might be four questions. I'm hoping for three questions only. Otherwise, four questions are like too much. Uh, right? And you have to explain and you have to keep speak. So it take a lot of time. But yeah, let's see how it goes. So let's try to solve this one. So there might be like four questions. You have like 2 hours to complete and all. So let's see. Uh, okay, so only three questions are there. Very good. So, okay, so this is the first question. Let's see what it says. So given a array, integer array, sorted in a non-decreasing order, means elements are in the increasing order. Remove the duplicates in place such that each unique element appear only once. The relative order of the elements should be kept the same. Then return the number of unique element in the num. Okay. Consider the number of unique element of nums to be k. To get accepted, you need to do the following thing. Change the array num such that the first k element of num contain the unique element in the order they were present in the nums. The remaining elements of num return k. Okay, understood. So what it says now? So we have to do this first thing is in place, right? We don't have to use any extra space, and that's why this question become good. So it says like this is the okay. Let me take this one, a smaller one first. Then later we can go on to this one. Nums. Okay. So the question says like you have to make sure you have to return an index, and basically what that index represent is all the elements till that index are all the unique elements in this in this array. Meaning here the currently these are the elements, right? In this array, but we have to first make this element like this 1, 2, and whatever remaining, and then we can simply return k. So k is like um 2, right? So like k is here. So it simply means before the k, we have all the unique elements in the array. So for example, in this case here, so all the unique elements will be look like something like this, like 0, 1, and then 2 and then 3 and then 4 and then others also, right? We don't have to care whatever outside of this k index. So now my k will be just after this 4, right? So before this k we have all the unique elements, and after this k or even at the k we don't care, right? So we just need to first make these elements to pull from the very end to the starting position all the unique elements, and we just need to return the k just to tell like okay, before k all these elements are here. Sorry. So and it is we have to do this in place, right? So in place meaning there is no way other apart from swapping, right? You have to perform the swap operation, and that is the only thing. Whenever you see like something like in place in the array based question, it's it's just a swap, right? Now how we gonna do that? And the good part is here that this array is sorted. So we can see the duplicates, right? We are iterating and we can check the duplicates on the fly. So that's the good thing. See, so the idea is very similar to two pointer. So what, how we gonna do that is, let's say initially my start k is equals to 0, right? Initially. Now I will start from this element here 0, and then I check this is 0 is already there in the very next time. Yes, 0 is already present, so we move. Then we go to this 0. Okay, let me move my cursor. I hope this is visible. Okay, let me zoom out. So initially I was here, right? K is equals my K is here, and my I is, let's say, variable is iterating from 0 to length of this array. And then we can check whether I and I plus 1 is same. Yes, it is the same. So we increment I. We don't move K, right? Then again we check, is I is equals to I plus 1? No. So this means this 0 needs to be at this position. So what I will do now, I will swap this 0 with the kth index, and I will increase my K also, and I will increase here. Now again, is I and I plus 1 is same? Yes. I plus 1 same. I plus 1 same? No. So I will move, basically I move this 1 to this kth position. Now here it will come like 1, and my K become like something like this. And then I will keep doing this. It's not very hard. I mean, so I hope this is clear. Okay, let me write solution for this, and then I can explain maybe one more time. Um, and we're gonna need two variables. I just need a K only. I can just return K, and simply I will iterate over each of these elements, n minus 1 I plus plus. Mm. And I can just, the thing that we had discussed, right? We have to check duplicates. So if I is less than n minus 1, then else K. So this is just for we are only able to move forward, right? Whenever I is less than n minus 1, otherwise we will get the out of bound index, right? So if uh, nums of I equals to nums of I plus 1, we can simply say continue. We don't need to do anything. Otherwise, now we know this, uh, where it is. So, so this is the case for this scenario. Like, okay, 0, we already have 0 in the next iteration, right? So we are not going to pick this one. We are going to pick the last one, right? And then we keep doing this. There may be other way for this one, sure, but I think this should work. So this will handle the duplicate. And so whenever I'm able to reach here, this simply means that I and I plus 1 is not same. So I can take this I, right, and swap it basically. So I can create a temp, maybe 0. Nums of I equals to nums of k. First, I need to temp is equals to nums of I. Simple swapping, right? Nums of k is equals to temp and then k plus. Okay. So let's try to understand this one, right? So initially we are at a 0 and I is less than n minus 1, right? And so nums of I is equals to nums of I plus 1. That's correct, right? 0 is equals to 0. So we are not going to take this 0 for now. We know that we already have a 0 in the very next iteration. So do we move forward? Now we check for this one, 0, 1. Is it nums I equals to nums I plus 1? No. So we will come here and I will basically swap this 0 with the very first k position. We're just trying to find all the unique element and move them in the very first position, right? So I will move this 0 and then I will move again. Now again I'm going to 1 1, right? And keep doing this. Now my only concern is what happened in the last. So let's say I'm here, right? 3 4, correct? Now at this 3 4 is not equal, so I will add 3. That's fine. Then I go to this 4, and so 4, this will loop will never run. That's fine. This if condition, and this 4. Yeah, this, I think this is it for this one. We just need to keep the swap thing. And this is very what we say, good algorithm. I mean, many problems, even if you solve that one, the quick sort where we have to do the partitioning based on pivot, we use very similar concept like partitioning of these elements, right? And I think we have some problem. Is it fine? I'm getting 2, and I think this is fine. Okay, let me try submitting. See if we have any compile time error. I'm not able to understand the solution actually. So here it says like my output is 2 and expected is like 1, 2. And why this is so? Uh, what I'm missing? Nums of I, the temp. Am I missing my swapping here? Nums of I, nums of k temp. That's fine. K plus plus. But okay, okay. Let me maybe I can just print the final array. I was not expecting wrong on this. This is like easy problem. But let's see what I'm missing. Okay, why I'm getting something like this? Something like this. Okay, I equals to 0, I less than n. This is the case when I'm seeing the duplicate. So I'm moving forward and then 1, 1, and this one. Uh, what? Something wrong with here? I don't know. Nums of A. Sorry. I will insert nums of k here. Now nums of k equals to nums of I and okay. I'm doing this swap and that's why it is getting messed up. Oh my god. I think I got why this is breaking. Because the element I'm transferring from the very left side. So here you see 1 1, that's fine. Then I'm going to 1 2, right? And then I'm putting this 1 2 here and this 1 2 here and moving forward. Hmm, no, okay. So this is the input 0 0. Not sure why it's breaking. Non suffice. Maybe maybe I can just print k also maybe. System dot out dot println k. Just want to see whether my k is moving or not. Yeah, so w- why this 2 is coming at the 0th place? I'm not getting. Nums of k, nums of I. 1, 1, 1, 2. Okay, I'm at this position and 0 this is equal, so I will continue. I will come at the 1st position. Now 1, 2 is not equal. Oh my god. What the hell? I messed up this condition so bad. And nums of I equals to nums of I plus 1. If this is the case, then continue. Otherwise, do this. Now I'm getting the output. I will explain why it was breaking. Okay, maybe I can. Okay, that's so silly. Okay, first let me submit it, then I will explain maybe. Mm. Oh my God. Okay, I will tell you. I have what why it was breaking, right? So let me I will copy this code here, and then I can explain, and then I can say, oh my, okay, I have to remove this. Okay. Now the problem was it's just very silly. So this if condition will always true, right? So whenever we go inside of this if condition, it doesn't matter whether this will run or not, like this one. We are never going to go inside of this else. And that was the problem. Meaning, whenever I is less than n minus 1, we are going inside of this if loop, right? And it doesn't matter whether this if loop executes or not, this else will never run. And that was the problem. So we have to make sure this thing and this thing together, if it's not happening, then we have to come inside of this else loop, and that's why it was the mistake I was doing. So yeah, I mean it took 15 minutes, 15 minutes, sorry, to solve this one. Oh my god. Okay, no problem. It happened. Hopefully we can cover by these problems, maybe solving faster. And this looks weird also, but yeah, let's see. A valid IP address consists of exactly four integers separated by a single dot. Now each integer is 0 to 255. That's fine. It cannot have leading 0. For example, 0, this is the valid IP. This is also valid. But this is not valid because here, right, it is like 011. So 0 in the very start is not allowed. um, this is also invalid because it contains like 312, right? We do not go beyond 255. And why this is wrong? Okay, we have add the rate, so that's why this is bad. Okay, so given a string S containing only digits, return all possible valid IP addresses that can be formed by inserting dot into S. You are not allowed to reorder or remove any digit in S. You may return a valid IP addresses in any order. Okay, okay. So it says we have a string, only digits are there. That's fine. Okay, and then we have to read it. I mean, on reading this problem, you will say it's a recursive based problem because we're gonna have this random chunk of numbers and we have to form all the valid IPs that we can form right from here. So and each integer must range in like this. So that's the important thing here, right? Okay, okay. Okay, so you must know recursion for solving this problem. So what's the idea? Idea is this one. Let me show you. I have, I like one of the problem I have solved similar kind of problem. Uh, maybe I don't remember. So the idea is, na, how you solve this. You have to basically generate all those valid IPs. So think of it like a recursive tree, right? So can I take two at the very first item? Yes. Can I take two five? Yes. Two five five? Yes. Two five five two? No. We cannot take anything beyond this because it will cross like 255. We have to go mostly 255, and then I can apply a dot. a dot, a dot, and then again for this two, now I have options to choose from this part, right? From 5, 5 to 5, 5. So can I add 5 here? Yes. Can I add 5, 5 here? Yes. Can I add 2.552 here? No. Right. And now it doesn't make sense to go beyond. Otherwise, all the numbers will cross this 552. So all the numbers will be in the thousands, which are not allowed. Similarly, for this, what we do the recursion, right? So I hope you get the idea, right? How we can just rewatch this part, and hopefully this will clear, right? So I will write the solution, then we can explain this one more time. So if you draw the recursive tree for such kind of problem, it will be very helpful to understand, really. So maybe let me create a list of string for storing our answer. You can just okay. Now, um, what? So I'm gonna call my DFS, my helper method, the recursive method. Sorry. And let's create this as a instance variable so that I don't need to pass inside of my DFS, right? So I can just pass like 0. So this is my starting from where I will start building my IP, and then I'm gonna pass an empty string. This empty will be keep track of the IP addresses we have formed so far, right? And yeah, this is it, I guess. So let's write our DFS. This is the starting PSF, I would say, path so far. So you get the idea, right? How we are doing this part. So initially I'm at 0th position, right? And I will try to build IP from 2, 2, 5, 2, 5, 5, and 2, 5, 5, 2. It's not possible, so I will not do that. So and that's the first recursive tree. So how we're gonna do that? Well, I'm gonna start my loop j from I j less than, maybe I can create n here, j less than n j plus plus. So 2, I will create a 2 and I recurse, then 2 5 recurse, 2 5 5 recurse, 2 5 5 2 recurse, and dot dot dot. And then in the next level recursion, we will try to build the path from that position, right? So this is the idea. And before that, we need to make sure we are not crossing um from like we are not crossing like 255, right? So I can just create a string builder here, sp new string builder, and sp dot append s dot char at j. And what's the value of this? Integer dot percent sb dot to string. This is to check whether we are not crossing, right, the 255 mark. So if x is less than equals to 255, then only we are going to recurse, otherwise we don't. And I can just select DFS. Now recurse from till j, I already taken till j, so I will say from j plus 1, and I will add the PSF, whatever path we have initially, add a dot followed by SP, right? I can PSF plus dot followed by SP. And one more thing, we have to make sure that our IP should not start with the 0, right? So um if here, okay, I will, maybe I can just add it in the base case, and that will work. And now if I equals to um s dot length, or maybe I can write it here since I already calculated n here, so I can write my base case here. If I equals to n, now the PSF will contain the valid IP we have built so far. I need to add it in my answer and then return. And one more thing, if um maybe I can put it here, something like this. If s dot char at I equals to 0, this means we cannot build anything. If the we are not allowed to start building IP from 0, right? Uh, okay, no, no, no. We can take 1 0, but we cannot take like 0 0 or 0 1 or 0 2, something like that. So that's why it's not allowed. So I cannot just write like this. If it is 0, then return. Um, if it, either this is the case, and I can say like x is greater than 0. How we can write? Uh, Maybe something like this. If x is greater than 0 and sb dot char at 0 equals to 0, then also continue. I mean, you can break basically. So this is the case. Okay, let me explain. So this is the case when, okay, when I'm taking the 0 for the very first time, my SB will contain like 0. I will start building from IP from 0 dot something, right? That's fine. But I cannot do something like this 0 0 or 0 1 and then dot. This is not allowed. So this condition will take care of that one. Like if x is greater than 0, whatever value we are building is greater than 0, or other it is not correct. I have to write like sp dot length is greater than 1. That's fine. And sb dot char at 0 equals to 0, we can break. It doesn't make sense to build an IP from 0, right? And in the last, if x is less than 255, then only we are going to recurse. That's fine. So I think this looks good to me. I mean, so for here you see, if we start from 2 and then that's fine, 2 dot, and then I try to build maybe 5. Okay, okay. And one more issue is we also gonna have exactly four integers separated by a single dot, right? So 1 2 3 1 2 3. There should be only three dots. So that is also very important. So how we can keep track of that? Uh, Maybe I can introduce one more variable to basically count the dots maybe. So for example, in this DFS here, I can pass a 0 also. So it basically contains dots. And whenever I'm doing this DFS, this means I have added one dot, right? So I can say dots plus one. And here I also need to check if I equals to n, that's fine. And if dots equals to 3, then only add to the answer, otherwise return. So I think this should work. This will take care of this basically configuring the IP in four parts. So if there are three dots, we are good. And all the numbers are between 0 and 255. So yeah, I think so. This is fine. Now one issue, one problem. So for this 0 0 0 case, you see, okay, I will take 0, I apply dot, 0, apply dot, 0, apply dot, and I will go to the here, and then I will also apply dot also here also. So that's not correct, right? So I can say something like this here. If j equals to um n minus 1, then don't apply this dot, right? So I can just say something like, I know it is getting messier a little bit, but it is like that. Else I will apply dot. So this condition is for this case, right? So 0 0 0 0. I'm now taking this 0 and my j is at n minus 1, right? And I do the DFS. Now for the very last element, I don't want to add that extra dot, and I don't need to do like dot plus 1 also. And for other part, I will add a dot and I will add, let's say like dot plus 1. Um, and I think I can write this part also a bit clean. I can remove this thing. I can remove. this thing and I can say if x is greater than 255 also break. There's no meaning of building an IP which is greater than 255. So I think this looks good now. Okay, let me compile it. See any compile time errors. Okay, no compile time errors, but I'm getting this extra dot in the very starting. Uh, uh, okay, but we are getting something very similar, so that's good. And okay, okay. Mm, so first we have to handle this initial dot. We don't want to add a dot at the very first time. So for that, I can write something like this. If j is equals to n minus 1 or j equals to I, no, 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 no. This is not that. Or PSF dot length equals to 0. Then basically add no, don't add any dots. So this let's compile it, and this should fix the first dot, I guess. Okay, we are getting so many. Oh my god. No, 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 no. Okay, that's good. We are able to remove the first dot. Now, why I'm getting so many valid IPs? Okay, let's see. And why in the first place I was able to take like 11135. This is very bigger than x. X here x is greater than 255. So it should break from this for loop. Uh, what? Okay, we have to debug this one also, I guess. Okay, let's see where it is breaking. First thing I want to fix is why we are able to take this 11135. So if you come here, we starting our J. I'm building a new string builder, appending a J, and I'm parsing it to an int value just to check whether it's crossing the limit or not. And this is for the zeroth case, that's fine. And if x is greater than 255, it should break. It should not run these things. So j plus 1, PSF plus SD, and here I'm saying like PSF plus dot plus SP. And I'm increasing the dot. Why this is not working? Oh, yeah, I'm missing something, but I'm not sure what I'm missing because I'm also seeing the valid answer. So you see here 255, 255, 11. Oh, okay. I hope this is visible, no? Yes, yes. So I'm also seeing the answers 11 and 135 and 11, 111 and then 35. But why I'm seeing these like 1135 is also coming as valid. This is also coming as valid. This is also something wrong with uh, here. And what's wrong? So I'm appending SB. I'm passing this X, and if SB dot length is greater than 1 and SB dot caret 0 breaks, that's good. We are doing this early pruning just to prevent some recursion tree. That's good. Now, why this condition? I'm not sure why. X is greater than 255. I'm breaking. We should not go beyond 255, but we are able to go like 1135. And if it breaks, it will go outside of this for loop, and that's fine. Mm, if j equals to n minus, why? Uh, why this thing is not working? Um, the rest of the thing is fine. Um, okay. Let me, I can just write this part. Why 1135 is coming here? If x equals to 11135, just print y println hello world whatever. Let's see. No, I'm not. Okay, I'm breaking here. That's good, but still I'm able to append something like 11135. My recursion is bad here. Okay, let me read this one more time. So this is my PSF that we are building. If I equals to n and dot 3, then we are able to basically divide this answer IP into four valid parts and then only add in the answer. So 252 and then 55 and then 255 and then 111. What's wrong? N is equals to s dot length I is equals to n. Okay, maybe I can just something like this. If sp dot length is greater than 3, system dot out system dot out dot println sp plus x. Oops, not like this. Plus x. I'm doing very silly mistake here, and I'm not sure where I'm messing this up. Oh, I mean, I'm not going. After this line, it is getting break, but somehow my DFS is broken, and where it is broken? Is it something related to mutation? I think so. I think something's wrong. So before breaking, maybe I can say like not sure. SB dot clear. Do we have a clear method? Or maybe I can do. I think we have like set length. Set length 0 and then break. And let's see. Still no. Okay, what's the third question by the way? Okay, third question looks minimum number of candy binary search kind of problem. Okay, hopefully we will. But why this is breaking? Uh, honestly, I don't know. I don't know why it's not working. Because if you see here, right, we are never adding anything that is greater than 3 size. But here I'm able to add like 11135. Is it okay? I'm thinking something's wrong here in this my line 31, 32, 33. I'm missing something with dots here. Let's see. If j equals to n minus 1 or my PSF length is 0, just append PSF plus SP and then dot. That's fine. The very first time we are adding, and this is the very last time. Otherwise, I'm doing j plus 1 PSF plus dot plus SB and then um dot plus 1. I think something's wrong here. Okay, let me write something like this maybe. Uh, DFS j plus 1, and I know that my SB is valid, so I can say PSF plus SB dot to string and dots plus 1. Or maybe, like, oh, I don't know. Maybe I can remove this dot thing. It is creating confusion to me. I can write an extra method to check whether an IP is valid or not. And if I run this code, I will know we will be having some extra dots, but okay, up here. Now I want to see what output we are getting. Now I'm not seeing any dot, and that's good. And this is because I missed my dot here. Uh, PSF dot plus. No, no, no. I can just select PSF plus this plus dot, and that's also I think correct. Run the code, bro. Oh my god. Yeah, that's fine. That's fine. Am I getting my valid IP also? So I'm seeing all these things, and that's fine. We can do the pruning because now I just need to validate whether my IPs are correct or not. So for that, I think it was a good idea if I have. Mm-mm-mm. No, I think dot was important. Otherwise, I have to write so many conditions here. D. Whenever I'm adding something, I'm saying D plus 1, and if D equals to 4, because I'm adding an extra D. If x is less than this or D is greater than 4, then also break. Now it is working. What the hell? Why it was not working initially? I just read the same thing, I guess. Three, four time maybe. Oh my god. Okay. Okay, now it's working, guys. So I just need to remove the last dot, so I can just say PSF dot substring from 1 to all. And this is it for the answer. So I'm, what? No, no, no. Okay. Spelling mistake. No problem. This is have to remove from the last, not from the starting. PSF dot substring from PSF dot length minus 1 from 0 to right. So 0 to this part. PSF dot length means pura, and this is, yeah, this is correct. Let's see. Okay, 255 getting. Let's check for others also. I'm not sure about. So 0000. We should get one IP with 0.0.0.0. That's good. I think now it will work for others also. So I hope you get the high level idea how this is working. But yeah, I don't know what I was messing up. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, that's correct. Let's submit it. Okay, yeah, we are able to solve this one. So I hope this one, the prerequisite for this one will be recursion, and I don't know what I was missing earlier. Maybe something here, something's wrong here. I was missing something. Otherwise, on the high level, I think you saw even the previous code was also very same. Uh, so yeah, you try to build the recursive tree, right? So something like this. So if this is the input, right, 2 5 5 5 5. So idea is I will at the first time I will take two, then 2 5, then 2 5 5, then 2 5 5 2, and this after this 2 5 5 2 there is no way we can build the valid IP because it will cross like 255. So we are gonna break. So we're gonna have like valid tree like something like this. Now in the next recursor part, from two we try to build something like two dot and then five. Oops, 2.5 and then 2.55 and then 2.55, oh sorry, 552 and dot dot dot. Similarly for 2 5 part we're gonna build like 25.5, 25 dot what is 52 and then 25.525 dot dot dot. Similarly for 255 for this level we're gonna do the again 255 dot 2, right, then 255 dot 25 dot dot dot. So if you build a recursive tree now, I hope you get the idea. So this is very you will see many problems related to this uh, recursive problem, right? It was long, I mean, messed up some conditions, but okay, let's see, let's try it. At least release this one quickly. So there are n children standing in a line. Each child is assigned a rating value given in the integer array rating. Okay. You are giving candies to those children subjected to the following requirements. Each child must have at least one candy. Now, the children with a higher rating get more candies than its neighbors. Okay. Now, return the minimum number of candies you need to have to distribute the candies to the children. Okay. Okay. This is I mean, you see here it is a optimization problem, right? Return the minimum number of candy, minimum, maximum, longest, shortest. So I have, I think, informed multiple times whenever you see something like this, optimization, there are some set of algorithms that comes. So first is greedy, then we have TP, then we have binary search, then BSF sometimes also works, and anything else. Uh, uh, uh. No, I think this four is fine. So you'd have to categorize the problem into these two four. So there is no other. If you solve optimization based problem, no, you will see most of them can be either with these or these or these or this. Greedy, DP, binary search, or BSF. Now the problem here is each child must have at least one candy, and children with a higher rating get more candies than their neighbors. So, for example, here the children are like 1, 2, 3. Children 1 has a rating of 1, children 2 has a rating of 0, children 3 has a rating of 2. So, we're gonna allocate the candies like 2, 1, 2, and that's correct because 1 is greater than 0, right? So, this children 1 has more candies than 1. Similarly, for this student, it has higher number than 0, so it has more candies than 0 also. And 5 is the minimum candies we can distribute. So I'm reading this, I'm seeing like binary search on answer based problem. Like if I take maybe I can something say like let's say my answer is 10. 10 is the minimum number of candies. So can I distribute 10 candies here in such a way that all the children will satisfy the above scenario or not. But it is not that much straightforward, that's for sure. It is not that straightforward. We have to, I think, apply some greedy also. How we gonna distribute the candies? And we cannot shuffle this rating and all. Hmm. I think the greedy way will be uh, to give uh, to start giving a candies to the student with as minimum as it could be, and that will be the one case. So, for example, let's come here, right? One, two, two. So, if I go to this, okay, I have to assign some candies to this one. What would be the most optimal? Can I assign one candy to it? We can. And what's the candy I have to assign here? I have to assign more candy. Okay, I can assign two. Now for this, what I can assign? So I just need to keep looking at the very left, and if I look carefully, it just feels like I can rearrange just with the candies, either one or two candies. I can rearrange, and that will be my answer. Is it? Even if I don't know. Like if you see here, we have to just make sure the students with a higher rating will get more candies, either from its left neighbor or the right neighbor. I mean, it just looks like a greedy. It's not like binary search or DP. Because if you see the question here also, it is getting like two and two candy, like one candy or two candy. Here also like one candy or two candy. And even from this rating 102, if it was like 11 and then maybe 10 and then maybe like 100, it's still the same. 212 will be the optimal. But how I can prove this thing? Each child must have at least one candy. Hmm. Mm-hmm. This okay. I will start from the very left and check his rating and the rating with the very next neighbor. Is it greater? Is it smaller? Or is it equal? So this is the three cases we're gonna have. Now in this case, this rating is greater than zero, right? So we cannot assign one because that will not work. So I have to assign, let's say, two. Then I come to here. This um, depending on the difference, I guess. So 102, that's fine. And this is 112. Okay. I don't think we have to do like so much complex thing on this one. Eight, first child, we allocate the first child, then second child, then third child. So we start giving like one candies to this one. We can give one candy? Yes. Can we give one candy to this one? No. Okay. Yeah, I think it's just a greedy thing. And first, I mean, in such kind of problem, what we have to do is first try to make such that the student on the very left side are satisfied, and then in the next iteration, maybe we start from the right side and make the other students also satisfied. So, I think It's just like a kind of like Moore's algorithm. We have Boyer-Moore algorithm, very similar, like two pass. So first I will try what I will try now. I will try to make sure I will iterate from left to right and try to assign candies, right? And then we can assign from, then we can move from right to left and assign candies and check whether we have valid scenario or not. I think that should work. It's just a greedy, right? It's not like DP binary search or BSF. So maybe I can say something like answer new int n. I can call this r maybe int n or the length. And the idea is first I will iterate from left to right, right? So something like this. I will basically check. I can just calculate the difference, which is like r of I minus r of I minus 1. So if you see here, in this case here, right, 1, 2, this means I have to give a smaller candies to student 0, right? So this simply means uh, if this is greater than 0, so 1, 2, the difference is like 1 and that is greater than 0. So whatever candy we have to assign more candies to this one, like the middle one, right? So for this one, right, you see here 1, 2, I'm checking for 2, right? Now 2 is greater than this one, so we have to assign more candies. So I can just say something like whatever candies you have, I have to in plus one candies, right? So something like this. Uh, answer of I equals to 1 plus answer of I minus 1. So it's just saying like whatever candies you have, I will have one more candies because we have to maintain the ordering based on rating. Now after doing this, I will iterate from right side now. Uh, I minus minus, and we don't have to think about edges, right? So that's why I'm going from n minus 2. And again, I will calculate the difference, which is like r of I plus 1 um, minus r of I. And if difference is greater than 0, now again the same logic. Now if here you see Ri plus 1, the next student has higher rating, so that student should get a more candies, right? So what will be the that? So that will be something like this. Answer of I. Uh, okay, one second. I'm missing something. No. I have to write like Ri and Ri plus 1. So, okay, let me see here. 2 is greater now here. In this case, Ri minus Ri plus 1, that's fine. And if the difference is greater than what candies I have to give to this I? So that will be method max of candies of I, comma, whatever candy the very next one has plus 1. Now I just need to return the sum of it. Return arrays dot same of answer dot sum. I'm not sure. Okay. So the idea here is I will first try to make sure the correct ordering of candies are assigned based on just comparing to the left of this neighbor. So for 0, I'm checking for 1. For 2, I'm checking for 0. And after assigning, I'm moving in the from the right side and I try to make balance out of it, right? So for example, for these middle neighbors, we still need to make sure they are also at the correct. So their ordering is correct, obviously based on their rating. So if you see for this one, 102, I will start from, of course, this one we are going to assign candies for this student later. It doesn't make sense, at least because there is nothing left to this one, right? So that's why we start from 1. We check from here. So 0, 1. Now 0 is not greater than uh, I minus 1. So that we're not going to assign anything for now. Then we go to this 2 and 0, and 2 is greater than 0. This is what we want. Now, so what we're going to do, we're going to assign whatever candies you have plus 1. So we're going to assign 1 candy. And then we can keep doing this from the opposite side and we balance it out. Let me compile it. Even I'm not sure about this one. So yeah, that's wrong. I'm getting 2. And why that is so? So we start from I and for I, that's fine. Answer of I, 1 plus answer of I minus 1, because I'm just taking to the left whatever candies you have plus 1. And then I'm iterating from the right side. And Ri is greater than Ri plus 1. That's fine. Yeah, I mean, this should work. I mean, why, for at least for this example, it's not working. Oh. Okay. No, no. We also gonna have a minimum candies we have to assign is 1, right? So if you see here, each child must have at least 1 candy. But for my scenario, I'm assigning like 0 also. So I mean, let's fill by default. Each student gonna have 1 candy in the initial time, and the later time we're gonna fill it up. That's not getting the correct one. Let's try submitting. Yeah, so yeah, I think it took like 1 hour. We stuck on this one for very long, and just because of my test if and if condition, right? And for this one, yeah, I think I don't know what I was messing it up, but ultimately, yeah, we are able to solve this one also. For this one, it's just a greedy, and if you have, I think I have solved such kind of problem where we have to do two for loop. Like when there is a question for a reordering of this array in some order, like 1 2 1 2 1 2, or some other questions I had solved, and they're also a very similar case, right? So yeah, that's the idea for these ones. Let's finish the session and see what questions were there. Okay, so this one is easy, and even we stuck for like 15 minutes. And this one, you see, it is hard, but actually, it was not hard if you know that most of the optimization problem, it is either like greedy, DP, right, binary search and all. And it took like 1 hour and 57 seconds for us to solve it. So I hope you like it. Uh, let's catch up in the next one. Thank you so much for watching.